Hey, party people, people who love to party. It's me, Mr. Beal, here to talk to you today about growth and decay problems. Now, hopefully you remember growth and decay from graphs that you've had to do in the past, hopefully the recent past. What we're going to be working on today is word problems that are associated with graphs like that. As you can see, we've got our exponential growth. As it goes from left to right, it gets really big as it goes to the right. The formula for that is the value of t being time, is equal to the initial amount times 1 plus the rate of increase to the power of the time that it is increased for. So once again, breaking this all apart, this right here is the value function with respect to t, so value over time. A is your initial amount. R is the rate of increase or rate of growth. And that's normally going to be expressed as a percent that we are going to convert to a decimal. And then T is the amount of time that we are talking about. So as we move on to this first problem, what we're looking for whenever we're looking for growth and decay, whenever we want to compare them, growth should be going up, either using the words growth specifically or increased or appreciated. All of those words are associated with growth. So here, listeria is a bacteria that is dangerous for pregnant women and people with compromised immune systems to consume and grows exponentially at a rate of 3.6% per hour. If a lab culture contains 2,000 individual bacteria, how many will be present in 3 days? Well, we're just going to plug this stuff in where it goes. We have V. We want to figure out our total amount of time that we're talking about. We want 3 days, but this thing compounds, or not compounds, I should say. It grows every hour. So how many hours are there in 3 days? Well, there's 24 hours in a day. 24 times 3 is going to make 72. So we're really looking for V of 72. Oh my goodness, it's going to have that many times to grow. We start off with 2,000, and we're going to times that by 1 plus the rate. Now we can't just put in 3.6 because percent, when it's got that little sign, that means it's actually smaller than it says right here. How much smaller? 2 decimal places smaller. So this is 0.036 to the power of 72. Now our next step, we're going to combine these guys, and you have to imagine that we are going to use the bejesus out of a calculator because I don't want to have to write on paper 1.036 to the 72nd power. That's going to be timesing that number by itself 72 times. Not gonna do it. Trusty calculator here. Calculator, can you help us out with this? I believe yes, I can. We are looking for a button that will allow us to take stuff to a power. That button could either look like a X to the Y, so like this, Y to the X, or in the case of my calculator, we've got the caret button, boop, and that will give us exponents. So I'm going to type in 1.036 to the power, there's my caret, of 72, and I'm going to hit equal. Bam! I get 12.7615, blah, 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 blah. That's how much this was right here. I'm now going to times it by 2,000. Voila, I've got, let's give myself some room here. I've got 2552, 3.03906. Geez, look at all those decimal places after that. Well, I'm looking for bacteria. So I just want to count, we're going to have to round this off to the nearest whole number. This is going to be 25523 approximately, because there's a 0 right after here. That's our nearest whole listeria bacteria. And when you're working with living things, you tend to want to round them off to the nearest whole because we don't count halves of stuff. In a lot of cases, there's not halves of things. We move it on up and you get the first example of my genius. Now in my cohort, wherever I go, wherever I am the #1 leading expert in interesting exponential word problems. Cobra McNuggets, the worldwide taste sensations, are coming fast are coming to fast food restaurant. Geez, I'm the one that wrote this, and I can't read it. So it seems like I'm not very much of an expert right now. Are coming to a fast food restaurant near you. We either need an A right here, or we would need an S over there. Yikes. Cobra McNuggets, the worldwide taste sensations, are coming to a fast food restaurant near you. If your uncle, Trombone Arthritis Williams III, increasingly consumes the delicious treat that no one can resist at an exponential rate of 5.9% per day, how many will he eat at the end of a week if he started with a 38 pack of Cobra Nuggets? So we're looking at V, and we want to map out our time. We're going per day, and we want a week. Well, how many days are in a week? We're looking at V of 7, not the equal sign. We need the parentheses. And this will be 38. There's our initial amount, times 1 plus, we're going to turn this into a decimal. Right now it's a percent. That means move the decimal place twice. 0.059 to the power of 7. It'll be 1.059 to the 7th times 38. I involve my trusty calculator Matron, and I tell it, yo, 1.059 to the 7th power. What you got for me? I've got 1.49, blah, 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 all that stuff, and I'm going to times it by 38. 56.76, approximately 56.7616, blah, 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 but we're just going to write 6 because this is another thing that we're going to take to the nearest whole number. Forget these half nuggets. We're talking about how many he does about. It's going to be approximately 57 nuggets that he's going to eat, Mr. Trombone Arthritis Williams III, on Saturday. Or I should say at the end of a week. We would have to have started on a Saturday to know that it's Saturday. Cobra McNuggets. Lowercase n. There we go. There we go. And the last one for growth. An NFT of a human butt inside of an oven made by the artist DiGiacomo Vespucci. Initially sold for $400. The next week it was sold again for $500. The week after that it was sold for $625. How much will it be worth a year from its original sell date? So what is going on here? Mr. Bill, I don't see any percents. Yeah, we're going to have to go figure out the percent, or we could just figure out what is being multiplied altogether. If you've worked with sequences at all, then the sequence that we're going to develop here would have to do with this T-chart. At 0, it's 400. At 1, it's 500. At 2, it's 650. And we're trying to figure out what we keep having to times by that gets us this new number. Well, how do I do that? Well, if you're looking at this, all you need to do is take this bad boy and divide it by this bad boy. It's 500 over 400, or look at that, 5/4. Now you want to verify this. What if we're wrong? What if that's not actually the pattern? We'll try it again. Is 5/4 times 500 650? 5/4 is about 1.25. So 500 times 1.25. Oh, snap. That's the number that we're looking for. Now you may be thinking, oh, that's the percent. That's the rate. No. Guys, stick with me. V is equal to, let's check out our time. Looks like we're dealing with weeks. How much will it be a year? So that would mean you would need to know how many weeks are in a year. There are 52 weeks in a year. So we're looking for V of 52. We started with 400, and then this number in here is 1.25, because that's what we're timesing by every single time. If you just wanted to know the percent of increase, it's 0.25, because we'd have 1 plus whatever the rate was. Now we're going to take that to the 52nd power, and it's going to give us probably a really big number, I would think. So I've got 1.25 to the 52nd. Wow. And then we're going to times that by 400. This seems Okay, that's something else. We've got 4379057.01. And we look and see if we can get rid of any of these decimal points. This number is, well, this number is money. We put a dollar sign in front. Start here, and every 3 we put a comma. This is $43,790,577.01. We would need 2 decimal places when we are dealing with money. That's good stuff. There you go, guys. There's growth. Now we need to do the opposite of growth, decay. Instead of our numbers getting bigger, we want them to get smaller, but we want them to get smaller exponentially. What that looks like in a graph is like this. It starts off big, but it gets small real fast, and it never gets past 0. We have all the same letters. If you're looking, we still have the value over time. We still have the initial amount. We've got the rate. In this case, it's rate of decay or rate of decrease, and our time. What really sets it about is that minus sign in between. That minus sign means that we are always going to get something that's smaller than 1. When we go and take that to powers, that makes it even smaller. Versus when we get something bigger than 1 and we take it to powers, it always gets bigger. Our first problem, relatively easy. A radioactive isotope decays at a rate of 6% per day. If the initial amount of the isotope material was 50 kilograms, how much will be left in 27 days? We're simply going to put the stuff where it goes. We got V. We look at our times, days and days. Nice, easy stuff. No extra calculations to make, just 27 days. Equals the initial amount, 50, times 1 minus, and that's 6%. Right now there's a decimal right here, and we're going to move it once, twice to be 0.06 to the power of 27. That's going to be 50.94 to the power of 27. And this should get smaller for us. When we take 0.94 to the 27th power, now I want something smaller. I got it, 0.1881, oh geez, all that stuff. And we're going to times that by 50 to get 9.406. Now we're approximating 9.406. Now, how much of those do we need? Well, this is a radioactive material. It's possible to have fractions of it and still make sense. But to make it easier on ourselves, why don't we round it to 1 decimal place? Right next to the 4 is a 0. This will be approximately 9.4. And we are good to go. 9.4 what? Kilograms of the material still. All right, now to show you my expertise, hopefully there are no more grammatical errors so that I actually look like an expert. Your grandmother's old beat-up car that she named Ugly Jeremy now sits in front of your house waiting for you to learn how to drive it, even though you already know how to hate it. If your grandmother scammed you out of $5,000 for it when she sold it to you, and it depreciates at a rate of 14.3% per month because of the family of scorpions that lives in the trunk, how much will it be worth in 2 years when your love interests lose interest in you because of the vehicle you drive? Also, the scorpions learned how to eat metal and are slowly devouring the car. Well, we just set it up like we normally do. We've got V of, we're looking for time, 2 years. Ooh, maybe we get to use the number 2 per month. Well, there are 12 months in a year. 2 times 12 is going to make V of 24. A little bit more difficult there. We've got the number 5,000. We've got the 1 minus, and we're looking for our rate. 14.3% turns into 0.143 to the power of 24. Let's see. Let's throw that all in a calculator. We've got 1 minus 0.143. That equals that. We're going to take it to the power of 24 to get that. And then we're finally going to times it by that initial amount, 5,000. Boop. I've got approximately 123.17135 and so on. What are we actually looking at though? It looks like we are looking at money. So this is going to be $123.17. And then we're going to stop it right there, rounding at the 1. That's how much the car is worth. You need to have a talk with your grandmother. All right, more decay. Let's get smaller and smaller. Last problem. My grandma, not your horrible grandmother, is losing a lot of weight because of oldness. 2 years ago on her 80th birthday, we picked her up and put her on a scale that read 340 pounds. Last year, we snuck up on her and weighed her, and she was 316.2 pounds. This year, we pretended to be ghosts, and she was 294.066 pounds. How much will she weigh when she's 150 years old? So we set up that same little chart. We can. There's other ways to do it, but I always like to look at a chart. It makes me feel, secure. 316.2 to 94.066. I want to know how I'm multiplying to these things over. I find that out by dividing. I'm going to divide 316.2 by 340. 316.2 divided by 340. Looks like I got 0.93. So that's what we think is happening times 0.93. We just need to verify it, that it happens on the next one. So 0.93 is right there. I'm going to times it by 316.2. That next value, we're timesing this by this to see if it gets that. That was a whole lot of bad English right there. Times 0.93. Yeah, it did it again. It did it again. We are good to go. That means I get to skip the part where I do the minusing 1. I know on the inside of my parentheses is 0.93. If I wanted to go backwards from there, I guess I could take this from 1 and I'd end up with 0.07. It looks like our original percent was 7%. Problem isn't asking me to do that though. So let's do what the problem asks, which is take this 340 pounds, multiply by this to a certain power that's going to be the same as our value of time. We're going to 150 years. Okay, where's the other time component? I guess it would be this 80th birthday. So that looks like 70 years is what we're working with. Dear Lord. All right, Grandma, you're making great strides in your weight loss. Let's see how that goes. We've got 0.93 to the power of 70. Okay, and then we're going to times that by 340. So apparently Grandma now weighs approximately 2.1148777982 pounds. I don't want to write all these numbers down, so what can I do instead? Well, I'm inclined to give Grandma as much as I can when it comes to this weight here. So we'll say 2.115. We'll take it to 3 places. I know I said 1 earlier, but I'm concerned now because my grandma weighs a little over 2 pounds. And that's how you work with word problems on growth and decay. Never seemed more prescient than it does right now, folks. Stay safe. World crazy.